We'll be going over section 10.5 today, area and arc length in polar coordinates. We're going to need to find where curves intersect. And so when you look at this at first glance, it might look like a system of equations where you can solve the system by substitution. So we could substitute in 1 minus cosine of theta in for r in this other equation. And so then we end up with the equation 1 minus the cosine of theta is equal to 1 plus the cosine of theta. And if we subtract 1 from both sides and add the cosine of theta to both sides, we get that the cosine of theta is equal to 0. I'm sorry, 2 cosine of theta is equal to 0. And so then we get that the cosine of theta is pi over 2, or 3 pi over 2 in the interval from 0 to 2 pi. The cosine of theta is 0 when theta is equal to pi over 2 or 3 pi over 2. And then the polar coordinates for the points that we get from this are we have theta, we need to figure out the r value. And so then our theta is how we write our polar coordinates. And when you put in pi over 2 or 3 pi over 2, you get an r value of 1. So you get pi over 2 comma r theta. Sorry. R is 1 and theta is pi over 2. And r is 1 and theta is 3 pi over 2. And so then the corresponding rectangular coordinates is that you're at the point 0, 1 and at the point 0, negative 1. But these two really are the only two r's and thetas that you can simultaneously substitute in to these two equations and have the same polar coordinates in the interval from 0 to 2 pi. The only problem is that's not what we're looking for. We're looking for where these two curves intersect. So we're looking for points, x, y, points where these two intersect. And these, they do intersect here. But if we look at the graphs, you'll see that both the 1 minus the cosine of theta and the 1 minus the sine of theta go through the pole. So for this one, r equals 1 minus the cosine of theta. When theta is 0, you're at the pole. And then when theta is pi over 2, you're here. So then this one right here is this one right here. But for this one, when theta is 0, 1 plus 1 is 2, you're not at the pole. You're over here. And then when theta goes to pi over 2, then you're at r value of 1. So that means that what we are looking at is this graph right here. And then this one goes like this. And you can see that when theta is pi, this curve right here is at the pole. When theta is pi, r is equal to 1 plus the cosine of pi. And so that is 0. And if r is 0, you're at the pole. And your polar coordinates for that are the coordinates pi comma, I'm sorry, r theta, 0 comma pi. And so then you missed that point of intersection, which was the pole. And the reason why you missed it is because you get it in two different spots. From this first curve, you get to the pole using the coordinates 0 for your angle, and that will give you a 0 for your radius, right? So r theta is the way these we write our polar coordinates. And so that's, you need to be careful with that. So how do we avoid that? Well, make sure you look at your graphs. You can draw your graphs by hand. You can use your graphing calculator to draw your graphs, but you need to look at the graphs. You can't just do the algebra like we did in the last slide. Okay. Next, we're going to move on to trying to find the area under a curve that is generated by a function where r is a function of theta, right? Now, what we're going to need is we're going to need the formula for the area of a sector. And so if you take a circle of radius r and you cut out a wedge from the circle, so that's what this is you have a circle of radius r and you cut out this edge. It turns out that the area of this sector is given to you by this formula. Area is equal to 1/2 the measure of the central angle theta times the square of the radius. And then if your angle is the entire circle, 2 pi, then this works out to be just pi r squared that we are familiar with. We get that formula. So what we're going to try and do now is try and find the area of a under the area of a curve as we vary our angle from an angle alpha to an angle beta. You can see then that as we vary our angle, we are going to, as my angle varies from an alpha, we're going to go through all these little areas here, and then we are going to try and calculate what is the value of this area here, right? And so our approach is going to be similar to what we did with trying to find the area under a curve by using rectangles, except now we're going to be using sectors, little wedges. And so what we're going to do is we're going to divide up our interval from alpha to beta into n little wedges, right? And that will be delta theta. That measure right there will be delta theta. That measure right there will be delta theta, and so on and so forth, right? Now, during each one of these intervals, the R value will not be the same, and that's what makes it different. But what we can do to get a good approximation is assume that our R value is the right endpoint right here, and then now we have this wedge, and then we have this wedge, and then we have this wedge, and so on and so forth, right? And so then the area of each one of these little wedges is given to me by the formula 1/2 r squared, which is, since r is f of theta squared, and then delta theta. And so then to get an approximation, we could add up all these little areas from these wedges, and it'll be the summation from I equals 1 to n of 1/2 r squared, I'm sorry, f of theta squared, delta theta. And then to find the exact area, we can take the limit as n goes off to infinity. So we'll take the limit as n goes off to infinity of the summation from I equals 1 to n of f of theta squared times delta theta. And then you should recognize this as a Riemann sum, and you should see that then this is going to become the definite integral from from alpha to beta of f of theta squared d theta. And that's our formula. So theorem 1013, area and polar coordinates. If f is continuous and non-negative on the interval from alpha to beta, where 0 is less than the value of b minus alpha, which is less than or equal to 2 pi, and all that's asking is that you don't form more than one complete revolution as you're going through from alpha to beta. And then the area of the region bounded by the graph of r equals f of theta between the radial lines theta equals alpha and theta equals beta is, and the formula is 1/2 r squared d theta. And so there we go. The difficult part in this is you have to know over what interval you integrate to generate the area. And so the way I like to look at it is what area or what angles do I vary this through for my radius here, for my radial line here, to sweep out that area. And so you can see that to sweep out this area, you're going to get that when this line goes from here to beta, right? So that's the tricky part. Okay. So find the area of the region described. The region inside the first quadrant with the cardioid r equals 1 plus the cosine of theta. The region in the first quadrant within the cardioid r equals 1 plus the cosine of theta. So again, this begins with a graph. We only want to be in the first quadrant. And I'm not going to make a table. You should make a table if you're not comfortable with this. I don't have room on this screen, so I'm just going to go ahead and start from, we'll hit the quadrant angles. When we start at 0, an angle of 0 gives me a cosine value of 1. 1 plus 1 is 2, and we're up here. When we get an angle of pi over 2, the cosine is 0, so we get an r value of 1. And so from 0 to pi over 2, the curve that I get traced out will connect these 2 points. And then once I get past pi over 2, then my r value is still positive, so I'm in the correct quadrant. But then for that time, I am in quadrant 2, and I only want it in the first quadrant. And so then at pi, I come back to 0, and so that's when I'm at the pole at a r value, at an angle value of pi. And then once I get past pi, then my r value is always positive because this is always bigger than 0, bigger than or equal to 0. And so then it goes like this, and then it connects back over here. Right, we've gone through these a lot slower. And so again, you're going to, the area that you're interested in is this area in this first quadrant. And you are going to sweep out that area with radial lines that start at an angle of 0 and end at an angle of pi over 2. So as you sweep this out, as you rotate this angle through this pi over 2, you sweep out that area. And so then now we're ready to set up our integral. We're forming the definite integral. We are going to sweep out that area as my angle varies from 0 to pi over 2 to be in the first quadrant. 0 starts me right here. The pi over 2 ends me right there, and I just sweep that out. Okay, and it's 1/2. The 1/2 we can bring outside, and then it's r squared. But r is 1 plus the cosine of theta, so it's 1 plus the cosine of theta squared d theta. And so then we just expand this. We can't do this without expanding this. We can't do a u substitution. There is no factor of the sine of theta to do a u substitution. We do a little bit of algebra, and this gets expanded to 1 plus 2 cosine theta plus cosine squared theta. Now for the 1 plus the 2 cosine theta, those have a basic antiderivative. For the cosine squared of theta, that does not, right? And so then that's why these formulas are up here, right? For the 1 plus, for the cosine squared of theta, we can exchange those, exchange that term for a term that does make it easier to integrate. 1 plus 2 cosine of theta plus, and then 1 plus the cosine of 2 theta, all divided by 2. I forgot my d theta. D theta. Now I'm going to factor out a 1/2 just to make the arithmetic a little easier. So that will give me a 1/4 out here. And then we have the definite integral from 0 to pi. And then I used to have a half. I factor out a half, and here's how you do that. You just ask yourself, a half times what will give me 1? And so that would have to be 2. And then a half times what will give me 2 cosine theta? So that'll have to be 4 cosine theta. And then a half times what will give me this? Well, I already have the, I factored out the half, so all that's left is the 1 plus the cosine of 2 theta. But the 1, I will combine it over here with this 2 and make that a 3. Right, so that's how we can do that. Now we can find the antiderivative, no problem. We have the quarter. The antiderivative of 3 is 3 theta. The antiderivative of the cosine of theta is the sine of theta for sine of theta. And rather than doing a u substitution, we're going to do this one in our head. What do I take the derivative of to get the cosine of 2 theta? Well, I need the sine of 2 theta, and then I would need an extra factor of 1/2 to cancel out the factor of 2 that's going to come out from that. And we're going to evaluate this from 0 to pi over 2. I forgot the over 2. Pi over 2. There we go. And then when we put in the pi over 2, we get 1/4 times 3 pi over 2. And then when we put in the pi over 2 into the 4 sine of theta, the sine of pi over 2 is 1, so we get plus 4. But when we double the pi over 2, we get pi, and the sine of pi is 0. So we don't get a third term for this term right here, because that becomes 0. Okay, and so now the sine, I'm sorry, when you put in 0, every one of those is 0, and so then this is minus 0. And so you get 3 pi over 8 plus 1. And I was able to fit it all on one slide. Okay, so let's move on. Okay, now find the area of the shaded region. Okay, so r equals 1 plus the cosine of theta. You should see that for the curve, r equals 1 plus the cosine of theta. When theta is 0, your r value is 2. And for this one, when theta is 0, your r value is 1. So this one here corresponds to this one, and this one here corresponds to this one. Now, another thing you might want to do is you might want to draw a generic wedge, just like we used to draw a generic triangle. Might want to draw a generic wedge. Your generic wedge is going to go from there. And you could see that the entire area of this wedge goes from the center to the outer curve to the 1 plus the cosine of theta. But we don't want the entire area. We don't want the area. We don't want this area right here. Right? So we want to subtract from that the area that is contained by the cosine of theta, the part of the wedge that comes from the cosine of theta. So here we're going to subtract some areas. So again, the entire area is going to be the definite integral from, well, obviously we're going to start at 0. That's what's going to give me this radial right there. And so that's a radial of 0. And we have to figure out how much do I have to rotate it to get all the way to over here, right? And so that comes when I'm back at the pole. And so at pi over 2, I'm here, not at the pole. But at pi, I'm at the pole. So this goes from 0 to pi. And then again, 1/2 r squared d theta. Right? Again, very similar to the last one, 1/2 integral from 0 to pi of 1 plus 2 cosine squared theta. Sorry, 1 plus 2 cosine theta plus cosine squared theta. Just expanding that trinomial, d theta. And so then again, using the identity, 1/2 the integral from 0 to pi of 1 plus 2 cosine theta plus 1 plus cosine 2 theta, all divided by 2 d theta. You don't have to do this, but we can again factor out a 1/2. Keeps the fractions down to a minimum, and you will get 2 plus 4 cosine theta plus the 1 plus the cosine of 2 theta, but the 1 we'll put over here with the 2, make that 3 d theta. Okay, and then basic antiderivatives now, almost a basic. This one's a little bit not basic. We have 3 theta, and then we have 4 sine theta, and then we have sine of 2 theta over 2. And we're evaluating this from 0 to pi. But when you put in pi, you get 3 pi, and these two become 0, because the sine of pi is 0 and the sine of 2 pi is 0. And when you put in 0, everything is 0. So the entire area is 3 pi over 4. But now, the area that is that you're excluding, you don't want any of that area generated by the circle. And so you have to subtract that away. So you have to figure out what that is. And so now we're going to find the area generated by the circle. And be careful, you have to go to the circle and decide what angles are going to generate that area. So let me erase all this, right? And so now we're trying to figure out what angles will generate this area. So how much do I sweep that radial in order to sweep out this area? And so obviously we're going to start at 0 because that's this bound right here. But I want to get back to the pole, and the pole happens at pi over 2. Okay. And so then this is just r squared, but r is the cosine of theta, so you get cosine squared of theta d theta. Again, we apply the formula because I can't do anything with that, so I just, the 1/2 is going to come out here. And you will have the 1 plus the cosine of 2 theta d theta. Basic antiderivative. So we'll go ahead and find the antiderivative now, leave that 1/2 outside. Theta plus sine of 2 theta over 2, and we're evaluating this from 0 to pi over 2. When we put in pi over 2, we get pi over 2. But when we put in pi over 2 over here, we get 0. And so then I forgot the 1/2 in my formula. And so then that would make this 1/4, right? And so it made that mistake, so that would be a 1/4. And so then this is also going to be 1/4. And then this will be plus, when you put in the pi over 2, you'll get sine of pi, which is 0. And when you put in the minus, when you put in the 0, you get 0, so there's nothing there. And so you get pi over 8. Again, your answer needs to make sense. The reason why I knew I made a mistake is because I knew that we had gone over that this was going to be a circle, and it was going to be a circle of radius 1/2, and the area of a circle of radius 1/2 is pi r squared, so that's pi over 4, but since we only have the top half of the circle, it's pi over 8. So I knew that I didn't have to do all this calculus. I could have just done it with pi over 8. So then the total area is to take the 3 pi over 4 and subtract the pi over 8, which is 6 pi over 8 minus pi over 8, 5 pi over 8. And again, was able to fit it into one slide. Okay, so find the area of the shaded region, right? So we want to find the area of the shaded region. And so if you draw a wedge here, let me draw it in red. If you draw a wedge here, you'll see that this wedge, the entire area is contained by the cardioid, right? And the cardioid is the 1 plus the cosine of theta, right? But once you get past that wedge and you're looking over here, now your wedge is contained only by the circle, right? So here there is no subtracting of areas. you are sweeping out your areas in two different ways. So starting from here to here, your area is only swept out by the cardioid. And then past there to the pole, your area is only swept out by the circle, right? So you have a cardioid and a circle, and so you need to be careful. So first thing we got to do is we got to figure out what angle corresponds to that point of intersection. We need that point of intersection. We got to figure out what angle corresponds to that, what ray is going to generate that. Okay, so to figure that out, we figure out where these two cross. We've already gone over how to do that. So we want 1 plus the cosine of theta to equal 3 cosine theta. So then that will be 1 will equal 2 cosine theta. Cosine of theta will equal 1/2. 30, 60, 90 triangle. 60 degrees, 30 degrees. This was 1, this was 2, this is the square root of 3. So we're looking at pi over 3. When theta is pi over 3, you will get to this point where both your R value, where your angle and R value will be the same. So you will have the same point. Okay. So then we have a sum of two areas. So the first area will go from angle of 0 to an angle of pi over 3. And this is all coming from the cardioid. 1 plus the cosine of theta. And so don't forget the 1/2 like I did on the previous one, squared, plus, then you have the angle from pi over 3, and we need to figure out how do I get back to the pole, right? And so to get back to the pole under the 3 cosine of theta, that is going to happen when the cosine of theta is 0, and so that happens at pi over 2. Don't forget the 1/2, r squared. And don't forget the d thetas. For this first integral, we've already done this exact same integrand 2 times, so I'm just going to jump to all the hoops. And so then this becomes 1/4 the antiderivative from 0 to pi over 3 of 3 plus 4 cosine theta plus cosine 2 theta. D theta. Same thing for this one. We're going to apply this formula up here. We can pull out the 9, so then we'll have 9/2 definite integral from pi over 3 to pi over 2. And we end up with 1 plus, we already had a 2 on there, so this is going to become a 4. And we will have 1 plus the cosine of 2 theta. D theta. So then this will become 1/4. The antiderivative of 3 is 3 theta plus 4 sine theta plus the sine of 2 theta all divided by 2, evaluated from 0 to pi over 3. And then plus 9/4 theta plus sine of 2 theta over 2 evaluated from pi over 3 to pi over 2. And so then when we put in the pi over 3, we get 1/4 times 3 times pi over 3 is just pi. Sine of pi over 3, sine of 60 degrees, square root of 3 over 2. So plus 4 times the square root of 3 over 2 plus 2 pi over 3, sine of 2 pi over 3 is also the square root of 3 over 2. So then you end up with the square root of 3 over 4. And when you put in 0, everything becomes 0. So we don't have to worry about that. And then plus 9/4. And when you put in pi over 2 for theta, you get pi over 2. But when you put in pi over 2 into the second term, you double it and you get pi, and the sine of pi is 0, so that goes away. And when you put in pi over 3 minus, you get pi over 3 plus the sine of 2 pi over 3 is again the square root of 3 over 2. And there you go. You can clean that up on your own. And there we go. Okay. Find the area of the region described. In the region outside the cardioid, r equals 2 minus 2 cosine theta, and inside the circle, r equals 4. All right. So again, this begins with a picture. Again, if you're not comfortable, you should make a table, as I showed you how to do in the last section. But when theta is 0, you're at the pole. 2 minus 2 cosine theta. Okay, so when theta is pi over 2, you end up at an r value of 2. So you're up here. Because of this 2, this expression here is always positive, right? So 1 minus the cosine of theta is always going to be positive, and so when you double that, that's still always positive. So then you're always in the correct quadrant. So when your angle goes from 0 to pi over 2, you're in quadrant 1, and you're connecting over here. Now at pi, cosine is -1, and so with that -2, that's going to give us a positive 4. And so then you're going to cross like that. And then at 3 pi over 2, we're back at 2. But an angle of 3 pi over 2, we'll put this down here. And then at 2 pi, we're going to connect back here. So that's what my cardioid looks like. And my circle of radius 4 is this thing right here. Try and draw the best circle that you can. And there you go. The region outside the cardioid, right? And inside the circle. And so then outside the cardioid and inside the circle, you can see that what you are talking about is all this area out here. And you can see that we can just take the entire area of the circle, which we don't need calculus for. That area is pi r squared. and then we can subtract the area of the cardioid. So if we figure out the area of the cardioid, we can subtract that from the area of the circle, and then we will be good. To figure out the area of the cardioid, you can use some symmetry. My cardioid does not look symmetric, but it should be, right? And so then all we have to do is figure out what is the area of the top half. So we can find the area of the top half using the formula 1/2. And then to sweep out the top half, we saw that we would go from 0 to pi, and then 2 minus 2 cosine theta squared d theta. Okay, but that's just the area of the top half. So then we'd have to double it. And so then that 1/2 goes away. And you just have the integral from 0 to pi of, to double this, we get, to square this, we get 4 minus 2 times 2 is 4, times 2 is 8 cosine theta, plus the square of the 2 cosine theta is 4 cosine squared theta d theta. And then you have the definite integral from 0 to pi of 4 minus 8 cosine theta, and you have the plus 4, and the cosine squared theta you can rewrite as 1 plus the cosine of 2 theta divided by 2 d theta. The 2's will cancel. Now we have the definite integral from 0 to pi. And when I distribute the 2, I will get a 2 from this one, and I'll add it with this 4 over here. That will give me 6. So it's 6 minus 8 cosine theta plus. And then the 2 gets distributed to the cosine 2 theta, and we get 2 cosine 2 theta d theta. And now we find the antiderivative. And so we get 6 theta minus 8 sine theta plus sine 2 theta, evaluated from 0 to pi. When you put in pi, you get 6 pi. And when you put in pi in for the angles, you get 0. And when you put in 0 in for the angles, you get 0. So the answer is just 6 pi. That's just the area of the cardioid. And so then the area of the region outside the cardioid and inside the circle is going to be pi r squared. My radius is 4, 16 pi minus 6 pi, and so the area is 10 pi. And there you go. All on one slide again. Yay. Okay. So if no segment of the curve represented by the parametric equations x equals x of t and y equals y of t is traced more than once as t increases from a to b, and if dx, dt, and dy, dt are continuous functions for a is less than t, which is less than b, and then the arc length L of the curve is given by this formula, dx dt squared plus dy dt squared. Now, if we have a parametric equation, we have a polar equation where r is equal to f of theta, then we can parameterize this curve by letting x equal r cosine theta, so f of theta cosine theta, and y is equal to r, which is f of theta sine theta, and now we have a parameterization. And if we apply this result to this parameterization, it'll take you a little bit. It'll get a little hairy because you have products there for dx dt and dy dt. But if you, and then you have to square those binomials and combine them and use some trigonometry. But then if you did all that, which I'm not going to, you would get to this formula. It turns out that let f be a function whose derivative is continuous on an interval from alpha to beta. The length of the graph of r equals f of theta from theta equals alpha to theta equals beta is given to you by the definite integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. So use formula 3 to calculate the arc length of the polar curve, right? So we want to use that formula to calculate the arc length of the polar curve when theta goes from 0 to 2. So S is equal to, S is for arc length, the definite integral from alpha 0 to beta 2 of the square root of f of theta squared, so e to the 3 theta squared plus f prime of theta squared. But the derivative of this is a composition, so the derivative e to the is e to the, same inside, 3 theta, times the derivative of the inside 3, and then this gets squared, d theta. And now this works out nicely because you get the definite integral from 0 to 2. E to the 3 theta, when you're raising a power to a power, you multiply the exponents. And so you get e to the 6 theta. And when you're squaring a product, you square both of them. So the 3 gets squared and becomes 9. The e to the 3 theta gets squared and becomes e to the 6 theta as well. You multiply the exponents. And now you have d theta. So now you have the definite integral from 0 to 2 of the square root of 10 e to the, these are like terms now, you can just combine them, e to the 6 theta. And then d theta, you can break this up as the square root of 10 times e to the 6 theta to the 1/2. So you have this constant factor of the square root of 10, 0 to 2, and e to the, or the square root of e to the 6 theta is e to the 3 theta, d theta. And then the antiderivative is square root of 10, and then e to the 3 theta over 3. And we're going to evaluate that from 0 to 2. And so then we have the square root of 10 all divided by 3, e to the 6th power minus 1. And there we go. Here's your homework for this section. This will be due next week, and we have an exam next week.